Programming a 3D engine is no small task. There are many approaches to three-dimensional graphics programming to project 3D-dimensional geometrical data to a normalized 2D screen. And what I hope to accomplish by the end of this series is to program a 3D game engine, the graphics and game mechanics side, over a period of time to create my own clone of the original Silent Hill PlayStation 1 game. A psychological horror game made by Team Silent, a development studio who produced some of the first completed Silent Hill installments from 1999 to 2004. Now, Silent Hill was a masterpiece of the early psychological horror genre of Japanese video games during the late 90s and early 2000s. It utilized fog and muddled lighting to mitigate the limitations of the hardware of the PS1, but this became essential to the horror experience of the game and became a trope for similar video games to follow. Now, you may be asking, why Silent Hill? Wouldn't it be easier to start off with a simpler game such as Minecraft or rudimentary form of 3D graphics such as Doom, Quake, or maybe even Super Mario 64 for the Nintendo 64 or any of those games? Well, the simplest reason is that I want to take on this challenge. This is what interests me the most. This game has taken an interest to me in early, low polygon, low res textures of this time period. This is a learning process for me, and it'll sort of serve as a journey, as you will see me tackle challenges head on that I've never encountered before. Because, truth be told, I'm a very least recent learner of 3D graphics programming, so I really have the bare essentials to get this started. So, this will be a sort of journey of me picking up more and throwing all of this new knowledge into this engine as I develop further. Now, I do hope to use this project to put whatever I learn into, and that being said, let's begin this journey, and I hope those who wish to program their own 3D graphics or game engine can make use of my code throughout this journey. Thank you. Alrighty, here are the videos that I've currently watched. I would like to have a big thank you to One Lone Coder and Ogldev. These are the two main channels that I've been watching to sort of start my progress on learning how to make a 3D game engine. I've already done some work, so these are things that I've been working on. So, but today we're going to start from scratch. So if we go to here, I've decided to call this game Whispers of the Fog, Silent Hill PS1 clone. Here I have some audio, some characters from the original series that I'll be using with some other ones from the GTA 3 game. For the most part, I plan to use almost everything from scratch, including my own textures and, for certain objects and certain buildings. But there are some things that I will use from the original game or from other games just to help me go along a little bit, because I know that I'm by no means a graphics programmer and I am not a 3D modeler. So there's only so much I can do. So to start this off, I guess we need to start off making the graphics engine side of the game before the game programming side, with the game mechanics, with the UI and the HUD and, the collision and the physics. So we're going to create a new project, application. What am I going to call this? I'm going to call this Silent Hill. So start off point. Package. Ryan Boots Games. Silent Hill. And that bad boy here. Stay here. This. Okay. Let's clean up all these header comments that I don't really need. So first off, first thing we should probably do is get a window started. So let's get a JFrame set up. Let's see. So JFrame, just gonna JFrame object, JFrame dot set size. Before I do that, let's see. Create data members. 800 will probably be fine. Height, I'll put as 600. Um, um, Title. What do I want the title of this game to be? The Spears of Fog, Silent Hill, PS1 clone. So size, width by height. Okay. Um, some other methods, set resizable. No, I do not want this to be resized because I'm going to use an aspect ratio that even though I could call it, for the meantime, I'm going to allow resizable to be false for now, just for now. So set the default close operation to be jframe exit on close. Dot set title. This title is a reference, and then jframe dot sets. Oh no! Why did that happen? Please no. Set location relative. Oh, I essentially want the actual JFrame to be in the middle of the screen. I don't want it to like pop up at the top right or the top left. Let's see. And then last but not least, we actually want to be able to see the JFrame. So I need to set the visibility, have a truth value of true. Go. Whispers of the Falk, Silent Hill PS1 clone. Should be fine. Ready? Next things next, I want to set up a class that's going to handle my rendering. I'm going to call it Game Panel. I want to thank a YouTuber by the name of Rye Snow. He helped me understand, multi-threading in Java and multi-execution programs and setting up a game loop. So I will be essentially using that like I always do. Thank you, Rye Snow. Okay, so this is going to the extension of the JPanel class is going to implement printable. Just get these imports in here real quick. I'm going to create a thread, game thread, and then I'm going to I'll create a double process number called FPS, and this is going to be, as you could probably assume, my frames per second. I'm going to create a constructor game panel that's going to initialize certain things. So I'm going to, for one, I want to have keyboard input. I want to actually make sure that the keyboard, that this class has access to the keyboard. And I'm going to set double buffering true as well. Next, I'm going to create a method to start my thread. Thread past this runnable. Then I'm going to start the thread once I call this method. Implement the run method. Alright, so let's create an instance of this class in the main class. We're going to want to add that to the frame. So all of our graphics are going to be displayed onto the panel. And I'm going to call that start game thread method. So once my main function is called, it'll know to start this game thread to repeat my code for the game loop. one last thing I want to do, create a method to handle painting onto the screen called the paint component method. I'm going to use instance of the graphics class. So clean up the graphics in. Oh, I see. I cannot spell. So, is what it is. Okay. So, in order for the main game loop, so while game thread is not equal to null, or while it exists, also methods. Do this real quick. This is going to fill the entire screen to be black. I'm going to do g.setColor, and I could do like call the color class like color.black, but I'm just going to create a new instance of the color class and input some RGB values. So 0, 0, 0. And that is essentially black. I'm going to fill the rect, so g.fillRect. It's going to fill a rectangle onto the screen. Starting from 0, 0, 800 by 600, or I can, for example, call the methods, I think, called getWidth. GetWidth, for example. Yeah, call that as well. Upon your constructor being initialized, it should be able to get those values from the JPanel. Okay, last thing, so interval equal to 1 billion seconds out of FPS, because I essentially want my thread to be running in nanoseconds to be as precise as possible. I could do it in milliseconds, but 1 billion nanoseconds is equal to 1 second divided by my FPS, meaning that I want something to be drawn every 60 seconds, since I set my FPS to 60. And then so that is unfortunately not where it ends for this loop. There's some other fundamentals that I need to do this. So I'm going to create a double called delta. I'm going to set it equal to 0. Long last time is going to be equal to, in the system, I can call the current time method to get the current time. Nano time, right? Or is it system dot nano time, I believe. Dot nano time should give me what I'm looking for. I'm going to create a long called current time, which is going to also use nano time, but I'm not going to define it yet. I'm going to set my timer, which is just going to be a counter, to be equal to 0. And then draw count is also going to be a counter that I'm going to assign the value of 0. So now that we have that, in this main loop here, we're going to set delta to, after each iteration, is going to add on the current time minus the last time divided by that draw interval. Oh, first I have to actually assign current time is going to be equal to system.nano time as well. Now we're going to set the timer to be almost the same thing, but it's just going to be the current time minus the last time. And then we're going to set last time equal to current time. Then, so we're going to say if delta is greater than or equal to 1, I essentially want to call my methods. Repaint is automatically understood by JPanel to be referring to this paint component method here. I need to create a method that'll handle some things. So I'm just going to call it update. And then after that, I'm going to decrement delta and then increment the draw count by 1. And then so last things first, I want to reset my timer counter. So if timer is greater than or equal to 1 billion, basically 1 second, I want to reset the draw count and the timer counters. Draw count will be 0. And timer will be equal to 0. And that should be the end of the loop. If I run this program, hopefully my screen will be filled black. Let me just for a second on RBT values. All right, I believe that is working just fine. Alrighty, so now that we have the main game loop set up, we have our main program running here. We can now finally start drawing graphics. The last little utility that I actually want is to be able to handle a little bit of user input or just prepare myself for that later down the line. So I'm going to create a class called keyHandler. Is going to handle the keyboard input. I'm also going to add mouse input and using an external library to have PlayStation 1 input because again, I'm very dedicated to this cause. So this class event event.key listener. So essentially this class is going to handle the keyboard input using the key listener interface, and then it's going to call the key event to get the keystrokes. This is just going to implement listener. So we're going to override these 3 main functions from that class. So first one is going to be press. The type, I believe. And the last one, I believe, is key release. I don't really use key type, but in order to properly implement the interface, I have to use this method. But I mainly am going to be using when you press a key and when a key is released, handle certain things. I'm going to create some booleans for now that I'll know I'll be using when I implement a camera. So I'm going to call it up press, press, front, back, turn. Won't really do much with those right now, but I know that I will be needing them eventually. All right, so next thing, I'm going to create some new packages. I'm going to call this one math. I'm going to call GFX for graphics. This one, game object. Create one for sound. And these are going to be the essentials that I'll need for now. So, make sure it's still recording. All right, perfect. Okay, so the first thing that we need to start starting from the graphics engine, because you have to do the graphics engine before you handle the game engine. So in order to get graphics drawn to a screen, we're going to use this math package here to sort of get some of the fundamental things that we'll need in any sort of graphics programming. And then so in 3D graphics, what I'm going to use is a technique that is called triangle rasterization. I'm going to create a software pipeline, a rasterizer that will essentially take triangles that can form the surface of well, can approximate the more triangles that you have the any 3D surface. It's a simple 2D primitive, the simplest one. There are convenient methods to draw and color them to the screen and to fill them. So the first thing that we are going to create is we're gonna create a class called Vec3D. Now, this is not a tutorial, but I will explain things that I know just in case. M More down the line, this is going to be me questioning my own self because I won't exactly know what I'm doing. So in Vec3D, we're going to have three double precision numbers called x, y, and z, and this is going to represent a coordinate in 3D space. I'm going to create a constructor to initialize these instance variables, x double y double z, x, x, this equals y, and then this dot z, z. So this represents a coordinate in 3D space. We're going to use this as the basis for everything that we do, to form, these vertices and project them to the screen and manipulate them to condense three-dimensional geometrical data to a normalized 2D screen. So the next thing that we need is a collection of these three vertices to create the surface of a triangle. I'm going to create a class that is called triangle, and it's going to group together three of these Vec3Ds. Call it Vec3D, Vec3D2, and Vec3D3. Again, going to create a constructor for this triangle to initialize these instance variables. I'm going to 3D, 3D, Vec3D2, and then Vec3D, Vec3D3. Ready? So this dot Vec3D3 is going to be two, and then this dot Vec3D3 is going to be, so this class groups together um three-dimensional vectors that will form the surface of a triangle, because any grouping of three vertices or three lines, should give you a triangle. Now we're going to create a class that is going to group together these triangles called a mesh. And the mesh is going to represent an actual object. A collection of these triangles, over so many of them, should form the surface of any three-dimensional object. So I'm going to together a list of triangles, or just a dynamic array of these, a collection triangles. I'm going to call tris, an array list. Actually, I'm going to need utility. Okay, and there's going to be a method that I'm going to add called load object from file. And essentially what this method is going to do is that there are these things in 3D graphics called OBJ files, or DAY files. They're essentially, in a program like Blender, you can essentially get 3D model information from these files. Also, a lot of them usually contain a PNG that represent the textures used for it. For example, this. So if I open this in Notepad++, I essentially get vertex data from it. I get the texture coordinates, and then I get the face mappings as well. And so I actually am going to want to load things from that. I'm going to come back here. I'm not going to do anything with this yet because I don't need it, but I do want to remember to actually create this in the future. So the last utility class I'm going to create is going to be called Matrix. Now I'm not going to go into too in-depth what a matrix is, but it's very important for 3D graphics. Essentially, most of the transformations, if not all of them really, that we're going to handle is going to be through this matrix class. Because if you take a vector and you multiply it by a set of 2D vectors, if you have a vector and you have like the vector stacked on top of each other, that's how you can handle advanced transformations. Because doing things line by line will become costly, especially for like I'm using a very, you know, cheap laptop that doesn't have a very strong GPU or graphics card. So this will become very handy for me to be able to use, matrix multiplication to handle all my transformations. So this class is going to hold, I'm just going to create a 2D double array that I'm going to call matrix. Going to be a 4x4. Again, must create my constructor. So now that we have these functions, we're going to start adding a couple utilities to them in order to make my life easy. Just for the sake of texture mapping, I'm going to create a class called vec2d that I'm not going to do anything with right now, but I'm going to oh my spelling just got infinitely worse. So, Q, then double E. Okay, and this is going to represent um a location onto a texture and grabbing from that, but that is not really concerning me right now. Couple more utilities I'm going to in the graphics package. I'm going to create a class called bitmap, which I won't do anything with, but I will need this next class called draw routines. I'm going to call it draw util. So this is going to be my utility functions that'll handle my drawing routine, so I don't have to clog up this main class that I handle all my rendering in. So in draw utils, I'm going to import graphics 2D. I'm going to java.on.geom.content. First function I'm going to have here is going to be the draw triangle function. Essentially going to take in three 2D coordinates to draw the surface of a triangle. Okay. Oh, let me forget. I need to pass a 2D graphics instance to be able to actually do this. So you draw new line 2D dot double. Keep this 3 times to form 3 lines. and I want to actually set the stroke, or another way to say this is to set the size of the lines to be 3. I actually want the lines to be quite full. Well, let me worry about this for right now. So x1. Oh, basic broke. Okay then. That's what happened. Okay, x2 y2. Then we're gonna 3. Ready? Gonna public void texture triangle, which I'll leave empty for now. But again, once it comes to texture mapping, which I'm not quite finished yet learning, but hopefully by this next episode I will be. But for now, let's just get some three-dimensional object projected to the screen. So let's come back here in this class and let's create some utility methods that we're going to use. So the first thing that I would like to do with a vec3d, I'm going to create a method that will return a vec3d. I'm going to call add vector. So it's going to take in two vec3ds and it's going to return the sum of them. I can just do return new vec3d in dot x plus dot x plus dot y plus dot z. Well, create the vec3d, then I'm going to call out. I'm going to initialize this. Well, let me not add all these spaces. Grab this. Well, oh, what am I doing? Yeah, I just had a huge brain fart. What am I doing? I don't know. I kept putting plus signs inside of commas. All right. So the next method that we're going to need is going to be called subtract vector. This is going to take the difference. I can essentially copy and paste this and just replace that with subtraction. Subtract, subtract, subtract. Next up is that we're going to want to multiply vectors. So I'm going to call it multiply vector. So it's going to take in a vector, and then it's going to multiply by some number f. I have a vec3d called out. Going to vec3d f f. And then we're going to return that output. So the same thing, I'm going to copy this We're going to call it divide, which is going to do the opposite operation. Instead of multiply, we're going to want to divide. Now that we have add, subtract, multiply, and divide, the next thing that we're going to need to do is a bit more complicated. Essentially, what I want to do is I want to create some methods that are going to take the length or magnitude, the dot product, and the cross product of a vector. So the first thing that we're going to be worried about is taking the dot product, which is essentially, the best way to explain it is checking how much one line projects upon another in order to see how similar the two lines are. And you sort of use that information to determine certain things about it, like maybe collision or what you should and should not be able to see. So we're going to create, that's going to be called dot product. I'm going to take in two input vectors. Oh, why? Oh, nope, it's not that. And now we're going to a vector called out. Essentially going to be, formula is going to be this. We got x n dot y times dot y n dot z times dot z. I don't know why I keep doing plus, but essentially this is what it is. This is sort of the formula for it. Space things out just for my own understanding in the future. It'll help me just in case I need to do a bit of debugging. And so now that we have the dot product checking how much one vector projects upon another, it would also be useful to be able to check the magnitude of something or get the length to turn it into a unit vector, which is essentially making things very simplistic to understand things in a -1 to 1 range. So 3D, that's going to be called um, length. Input. And so essentially what this is going to do is give ourselves output vector, 3D, and it's going to be on the square root of the dot product. And this should essentially give you the magnitude. All right. The dot product should be a number. It should not be a vec3d. Yes. Yes, the dot product should definitely return a number. Like a right. Oh, right. That's why I added the plus signs this time. Again, I'm a bit scatterbrained right now. I'm guessing the length should also, I'm assuming, get it to be a unit vector. I'm actually going to check that right now, just to make sure. I don't want that to come and bite me later. I'm actually going to go and check this real quick. Okay, good, good, good. Okay, so the next thing I want to be able to do is I want to normalize um some sort of vector. And to normalize something, after getting the unit vector of the length, essentially what you want to do, how to explain normalizing. Well, let's just say that it's something that you have to do. You want to normalize it. So this will return. It's going to be able to normalize. Taking some input and to normalize, I need to take this bubble and I'm going to call it length here. And this will normalize it. And the last one that we'll need for now, after normalizing, is taking the cross product. I do not know how to derive the cross product anymore as well as I used to, so my current understanding of it is probably rudimentary, but good enough. And essentially what the cross product does is it takes advantage of the three-dimensional geometrical data and returns the surface normals to an object. So the perpendicular line from that extends from a plane of a particular surface. And so the formula for that, call it cross product. Taking these. Now, if I recall correctly, it is essentially going to create an output vector. Essentially, out.x is going to be equal. Was it actually? Need to think about this for a second. I guess you can say in dot y times in2 dot z plus in dot z plus 2 dot y. And space this out for my own sanity. Multiply. So out dot y is going to be equal to n dot z times n2 dot x x times z. Is going to be 2 n dot x times 2 dot y plus n dot y times n2 dot x. And then just so these are the utility methods that we'll be using to add, subtract, multiply, divide vectors, getting the dot product, the length, normalized, and the cross product. These are by far the most important because they're the most fundamental um, linear algebraic equations that we'll be needing to basically do everything in the graphics and the game mechanics side of the engine. So the next thing we're going to do is we're going to go to the matrix class. So The first thing that we need to do is set up what I was discussing earlier is multiplying a vector by a matrix. So we'll return a matrix, so public matrix, multiply matrix vector. Multiply a vector by the matrix. So I'm gonna need to give it an input vector, an output vector, and you're gonna need it to give it a matrix. And then so formula for that will be the output. There's a certain formula that you can go by for any sort of matrix multiplication. So while certain inputs would be different, essentially the formula for how you derive such like the rules of the matrix by vector multiplication will always follow like this same rule. So we're going to take the input's x value, multiply it, we're going to call the matrix of that. So 0, 0. Because essentially what you're saying is that, if you had it like if you had four different lines, right? So first line is X, then Y, then Z, then this mysterious fourth dimensional pan-dimensional trickery to cast down the essential shadow of a 3D object to handle some sort of discrepancy back to the three-dimensional world. Very odd things that I don't completely understand, but I accept it as fact. For all there is to it. So we're going to take that Y, I'm going to multiply it by 1, 0. This is the next line to handle the Y. Then the Z is going to be that next line. And then we're going to add this mysterious fourth dimensional element. I'm going to copy and paste this. And this to the Z. Two, 3, 1, 3, 1. So essentially, the scenario that we're going to want to handle is that if this fourth dimensional, trickery, is not equal to 0, we essentially want to divide everything by that. So out.x divided by w. Let me not forget any of my actual mathematical operators. I like how I said this was supposed to return a matrix, but this actually is supposed to return a vector. Okay, so that's gonna handle matrix and vector multiplication. So the next method that we're going to need is now going to be getting into how do we condense three-dimensional geometrical data to a normalized 2D screen. And that, my friends, is where we get into what is called the projection matrix. And then so a simplistic rundown for it is that there are some assumptions that you need to understand about how you're going to handle the projecting of this three-dimensional data to a normalized 2D screen. So the first thing that you want, this is going to actually return a matrix this time. And I'm going to call it projection matrix. So essentially, this is what projection is. There are multiple kinds of projections, but we want what's called perspective projection. And essentially what that means is that we want to um, account for as close as possible a first person user's eye perspective. I'm going to develop a first person shooter stock camera simply because that's what the one lone coder made, and that is what Ogldev made. So I'm not actually don't know how to make any other types of cameras, but essentially what this projection matrix does is that it takes what is called the view frustum, and then it takes some assumptions regarding the aspect ratio to normalize a 2D screen. Um, it takes the field of view and the relational field of view in order to map um, points onto the screen from the 3D world and um, operations on it. So some input that's going to be needed is going to be called, first thing that I say we need is we're going to need the near plane, the furthest clip plane that we want for objects to be able to be rendered. Going to want the aspect ratio, and then we're going to want the field of view. We're going to initialize matrix. We're just going to call it mat. Just populating this 2D array real quick. Okay, so for this projection matrix, I'm going to create a double that's going to be called FFOV, which is going to be that relational field of view that is going to help map the field of view, let's say if it were 90 degrees, in order to map the relationship for zooming in and for zooming out. So it's going to take that field of view, that angle that's given. So it's going to be 1 over that field of half of the field of view, because the view frustum you can divide it into 2 right triangles, and I'm going to want I want this to be in radians. That's basically what this is here. So deriving the rest of the projection matrix. So of course, the first thing that you decide is that you want to normalize that 2D screen. So effectively, this aspect ratio is that if I decided to let my application be resizable, I want to transform and scale anything that happens, any object inside of my 3D world to this screen according to this aspect ratio. So if I wanted to increase my screen, if everything inside stayed the same, that would be bad. If I made my screen smaller, since screens can vary in size, if I made it smaller and nothing mapped according to that, that would be a problem. So that's what this aspect ratio handles. The far and near clip planes are essentially handling rendering and normalizing depth, or the z value. And of course, this FOV is again mapping the relationship that the user can experience with, zooming in and zooming out essentially. And this handles like the vast majority of the graphics engine. This projection matrix is by far the most fundamental thing needed from anything to do with projection. The first thing here is that we're going to call mat.matrix. So 0, 0, that first x location is simply going to be equal to this aspect ratio times this relational field of view. The next thing that we're going to be worried about, I believe, going to be 1, 1. is essentially going to be just that relational field of view. This is just going to affect the y. Next thing, leave of a thing. So if it's in the z, it's going to be 2, 0, 1, 2. So 2, 2, I believe, where this should be. And it's going to be f far divided by f, f near. So essentially what this does is that what it's saying is that if we wanted to define where our 3D point in terms of depth, its z point exists inside of our normalized screen space, essentially we're going to want to take the furthest distance it could be, the closest distance it could be, and we want to scale that back up so that we say that it exists in our plane, not a value between 0 and 1, and that's where it should exist. And so, by that logic, there's one last thing that we need to account for. I'm just going to do 2, 3 here to be equal. So at 3, 2, we're going to need to handle a small discrepancy between the player's eye and the actual screen. And this here should be projection matrix. Now I'm actually going to go and check my notes if that is correct. Very problematic if that is the case. So I've messed up anything here. Alright, so this is the projection matrix. Again, check out One Lone Coder's video and Dev, and they will explain this in far greater detail. Great, videos for this. I want to thank them so much for being able to actually get me to this point at all. So check out One Lone Coder's videos. He talks about the projection triangles and perspective projection. So now, let's see how long this has been going on. Around almost an hour now. So the next thing that I'll actually want to code in or method is going to be rotation matrices. Now these can be found online. Most of these transformations I'm getting here. Um, there's a site called Learn OpenGL, which kind of goes over most of these transformations. The central transformations that you want to do on any triangle is going to be rotation, scaling, and then translation, which have different operations that you need to perform on them to get those things. And so rotation is going to be multiplication matrices. And so the reason why I want to be able to rotate in the X, Y, or Z direction is that I want to get some perspective going on, to be able to see different parts of this theoretical thing that exists in 3D space. That is essentially why. So the first thing I want to do is I want to return a matrix, going to be called rotation matrix X. So you're going to put an angle in here to handle the cosine and sine. I'm actually going to grab this down here. So say that matrix of 0, 0, 1. These are pretty standard. They can be found online. I don't know how to derive them. I understand a bit of the trigonometry behind specifically the X and Y rotations, not the Z. I've never really dealt with that outside of 3D calculus, which I don't remember much about, to be honest. So 1, 1 is going to be math.cosine of this angle. Next, I believe is going to be 1, 2. going to be equal to sine of that angle. 1 going to be negative sine of that. So the last one, 2, 2 is going to be sine angle 3, 3. We're going to want to return that matrix. So next, matrix in the y, angle value, copy this, and change some of the values. So in the y, 0, 0 is going to be cosine angle. Next is going to be 0, 2 is going to be sine that 2, 0, negative sine, and we're going to have 1, 1, 1, going to have 2, 2 to be equal to math.cosine, and then 3, 3 is 1. So that is next method, matrix, matrix in the zeta. Okay, so 0, 0 is going to be math.cosine, 0, 1 going to be math.sine, next one's going to be negative math.sine. 1, that would be a 1, 0. 1, 1, it's going to be math.sine of the angle. Then 2, 2 is going to be equal to 1, and 3, 3 is okay. For a lot of utilities, oh, and there's still one more. It's going to be matrix multiplication. Now, the previous one that we did was matrix by vector multiplication. So matrix multiplication essentially is going to combine multiple transformations that we want to do, like a rotation in the x or z direction or projection matrix. We wanted to combine all that, a translation matrix. And it's going to combine all of that into one matrix that's going to contain all of the transformations handled, which is very convenient. It essentially takes down the computing power so much to be able to do it that way. So lastly, I'm going to create a translation matrix. Now I said we're done. Almost forgot. Also need to do an identity matrix. A lot of matrices here. A lot of these. Okay. Here's going to be 1. One is going to be 1. 1. 3 is that, and that should be the identity matrix. This is going to be the translation matrix to handle the translation operation. Was the one, I think essentially it's just this. This is going to translate if you want it to be in the X, Y, or Z direction. Okay, so I'm going to check that because again, it can be very problematic if any of these are wrong. Let me check here. So, 3 is okay. Not much a huge bullet there. Public. Um, oh yes, matrix. Taking 2 matrices as input. Oops, forgot about that. Let me grab this again, please. Appreciate that. First, so reverse through some of the elements. So 0, C is. We're only gonna handle 2 at a time. Nested for loops. So R 0 as long as R is. Unfortunately, this could only hold maximum. We're only gonna deal with, fourth dimensional array. So say that matrix C to 1 dot matrix of 0 times M2 dot matrix C matrix 1 times 2 dot matrix C plus this line dot matrix 2 dot matrix C of 3 M dot matrix. That's sort of the rules for matrix multiplication. It's a lot. A lot of this is mainly getting all the utility functions that I need. But now let's actually get to what I originally wanted to do, which was drawing something to the screen. First thing is we're going to go into define our projection matrix data. Let's say our near plane is going to be 1. Our far plane I'm just going to set to 1000. I'm going to set FOB to be 90 degrees. And then our aspect ratio this. Go to view, nearest plane. Do this plane. Now we're going to create an instance. We're going to create call it mat. Just create an empty constructor. Mat for me, please. Thank you. Matrix. Add proj, which is going to be our projection matrix. Projection. This is going to be our projection matrix. So you just here just for later. H. Handler. And this. What this class is a class that handles the keyboard input. I'm going to create a method called Initialize Mesh. And essentially what this method is going to do is that I'm going to create a mesh object from an object. So I'm going to create a mesh. I'm going to cube that. And so I'm going to say that mesh cube is going to be equal to a new mesh, and I'm going to as list create an array of triangles. Ready? And I'm actually going to borrow. I actually don't want to type this out, but I essentially am going to take the coordinates of a unit cube. So a cube in that goes 1 in any sort of direction. So I'm going to come here and take this data quick. That. Actually, this is a very bad idea. I forgot that that project that I was working on was quite a bit more advanced than this one, so I need to delete some of this jargon that I don't need. A moment to delete all of Jargon. I was already at 1. I was about to say that could have been very bad. So essentially what this cube is that it's going to be an array of triangles that are going to take together a collection of vertices that are going to form on the surface of an object through the triangles. So make sure that I'm grabbing all of this. I think that should almost everything, right? Is it that I'm missing something? I want to actually go and check back here. So what am I missing? Oh, I see. Um, yes. That is something fairly major. Let me check, make sure all my commas are here. Comma, 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 comma. And then curly brace. That did not fix my issues. I'm literally just going to do what opens up triangle array. Triangle and wait a minute. No. That's I believe. Nope. Okay, yeah, there it goes. I knew that that had to be happened for a second. Okay, so this is going to represent the cube. So I grouped together the cube using the conventions of the south, east, north, west, top, and bottom. So this is going to be the forward face that we can see. This is going to be the face facing the east direction, the north direction, west, top, and bottom, and so on and so forth. I'm gonna call this in a constructor here. Initialize mesh. Initialize mesh. I'm here in a drawing routine. For each loop that'll traverse. So each triangle try. I don't know why I do this. I have to be able to access it. Triangle, the first thing we want to do is we're gonna We're going to want to get an output vector. It's going to call it triangle. Called try projected. Is essentially what I'm going to do. Projected. I want to check to see if my projection matrix is working and if I actually get something drawn to the screen. Oh, that going. So all my drawing routines. So I think it should be in draw utils. Triangle. Um, in my draw utils. Okay. All you. Let me see if it'll automatically import. Ugh, I have to do it myself. So dot. Now what is it? Um, what? Get rid of it. Oh, I almost forgot. An instance of graphics 2D class. So, projected. Projected. But I let's see if anything can be drawn to the screen. And here we go. So the reason why this little baby pixel has been drawn to the screen is that essentially the projection matrix will always return values between -1 and 1. That is sort of viewing with your view frustum. That's what you want. you essentially want into this projection plane for things to be drawn between -1 and 1. And so because this is so small here, we actually need to scale this to be bigger to the screen. So the first thing that we're going to do is that I projected x plus equals 1. We want values to be between not -1, but between we essentially want the values between to be 0 and 2 instead. This and then I will do the same for the y. And then try half of the, for the x, it's going to be the screen height, no, the screen width, so it's 100. Y is half of the screen, 600. We can do this for each x. Now this should be scaled to a larger view for us to see. Oops. That I just did not quite do that right. Let me think. Um, okay. Plus equals 1, then times equals x. Question now is why didn't that happen? Something I fundamentally did wrong. I have to think about it for a second. Alrighty. Let me think. I'm going to go and check the video real quick so I don't make this mistake
Hello.
again. This is a fairly embarrassing mistake. This is very early to me making this sort of error. Hmm. Don't understand why this. Going to go here, go and check to see why that happened. I don't like constantly having to go back and check over and over again because it makes me feel like I didn't learn anything. Hmm. Let me do something. I'm gonna create. I'm gonna recreate this here. Right triangle. Just had to make sure that it wasn't because of the, that could have been confusing. Let's see. Vec 3D.x, vec 3D.y, 2.x, 2. Hmm. So I've translated it. This. I'm confused. I'm gonna comment this out for a second. Leave it like this. Comment about it. Should have been scaled into view. I don't understand. I don't understand what I'm doing wrong here. It should have been scaled into view. I don't think this will have any bearing on anything. It could. X's and the Y should be added by 1. Yeah. It should theoretically scale. That's not what's happening. I have to think about why that's not happening. 3D. All the x's are y is implicit. X's should be multiplied equals half. Hmm? I wonder. So I think the way I set this up should be input, output. But it could be in my projection matrix. This could be the problem right here. Let me go check back to that projection. So, 3, 3 should be 0. Well, didn't I check this earlier? I'm gonna come back here. projection matrix. And I'm just going to borrow this. I think this should be. Oh boy. um, 3, 2. I'm gonna swap these for. And there we go. This is finally I figured out what was wrong. I knew it, my projection matrix. I was looking at the reading it wrong. For some reason I'm really bad at reading 2D arrays. And I was looking at a transformation on like another screen without actually looking at like the element, the specific element. So now that this has been um scaled into view, the thing that we don't have is any sort of perception to 3D. As far as we're concerned, this we have no relevance of what this item could be. So the next thing that we need to do after scaling it into view is we're going to want to translate this um to be a certain amount of units. Um but before that, I'm going to create another matrix. I'm going to call this the rotation matrices. At Z at ZX. So this is going to be rotation of Z and X axis. And then I'm going to create, so this is going to be angle used in rotation. C's, call it theta. Theta is usually the Greek term used for handling the trigonometric angles, an angle. So here I'm going to at Z's matrix in the Z. X is going to be rotation matrix X direction. Then we're just going to increment theta 0, 0, 2. So now that we've done that, I'm actually going to need another triangle. I'm going to call it try-trans for try-translated. Don't take that out of context. Essentially, we're going to, before I do any matrix multiplication, I want to do these one at a time. So I'm going to create, actually, no, I'm just going to do the matrix. Well, no, I'm going to call it the triangle. Mat rod Z. Stand for the rotation in the Z, and then at ZX. So at the by matrix vector, input's going to be try, output's going to be mat rod Z. keep this for each vertex to have the transformations on each one. Then I'm going to take that, instead of try, we're going to put mat.z. So now that we've rotated in the Z, I'm going to take that. Now we're going to rotate it, take that Z, and now rotate it in the X direction afterwards. Two, three. Use X matrix. So now that we've rotated it, now we want to translate it. The order of operations for this does have a lot of importance. Now we're going to set try trans to be equal to mat rot zx. Then we're going to do try trans vector.z is going to be patient dot z plus 3. So we're going to want to translate it 3 units, in the z direction to give it depth in front of us. Input should be try trans out. After that should come out try. Now, oh, there's some more things we need to handle for this cube, don't we, huh? Now we need to consider what. First thing we needed to do is rotation matrices. We needed to rotate in a Z, rotate in a X, translate, use translation. Mm-hmm. Do this. Also could be okay. I'm trying to think. The first thing that you need to do is you need to rotate, right? Let's go look at these transformations. You rotate in the X, rotate in the Z, translate that, and you project it. So this is probably where it goes. I think the try gets corrupted as it gets used. The multiply matrix vector. I don't think it should though. But say I'm going to initialize here. I think I know what happened again. I think the matrix code again. I think it's this. There, okay, that's better. I want that bad boy pushed a bit further back so we can get a bit of a stronger understanding of what's going on. Hmm. Yeah, so I'm gonna go ahead and create that world matrix now. I want to create a matrix called that world. That world is going to be a matrix. So you can call them so really. Oh wait, not for that one. Not for that one. I didn't initialize that. Can't do it then. Okay, so now I'm going to do mat that world dot Atrix matrix multiplication. It's going to first take in that z, that zx, I believe. Um, it's then going to take in matrix multiplication between that. I'm going to create a matrix. I'm going to handle that translation. Now that we have this world matrix, I don't need these rotation matrices anymore because I'm not going to use them. Um, I believe before projecting, just call projected by this. I believe. Let me check that. This one, actually, I can do take the translated view. So I can take this translated view, I set up my matrix. This is also consider how long this is, almost 2 hours now. Geez, I projected try transcribe. I'm gonna look at this. Rid of these for a second. If I go back here, I go to ah, so turn in vector. Then after doing this, after translating them, after accumulating all those transformations, I think now I can I, right? I can do that for text as well. Oh boy. Back to my matrix. Translate that around 16 units. There we go. Here is a cube. Rendering is not very smooth, so that's going to be a problem. I understand why that is, but for now, this is what it should look like. This I'm going to be dealing with for the moment. So yeah, we have a 3D cube projected onto the screen. I'm quite happy with this. Little things I need to do because sort of lagging, and that's probably gonna annoy me. That's how so I'm gonna one last time go and check Atrix That's how I'm handling everything, making sure this is correct. Zero. Be happy with that. Makes a lot of sense. Actually going to draw utils and comment out this line for a second. That happens if I set this to 2. That's much better. I like it more 2. Alrighty, let me see. Is that where I want to end it for today? I like to keep on this. So I guess from my own understanding, Atrix Multiplication simulates multiple transformations. Matrices. The matrix. Here we have 2 triangles, triprojected, tritrans. So we're gonna use this translated to accumulate for each triangle inside of our mesh. Going to multiply that by all the accumulations of the transformations. We're then going to project that, take that data, and then put it in the projection matrix to project it to the screen, and then scale it into view. And those are the primary transformations that we've covered up to now. Now we have this rotating cube. So possibly next episode, what we're going to handle is culling normal data and making sure that things are drawn properly on what we can and cannot see using the cross and dot product. But for now, I think that's where I will call it a day.